Hello and welcome back. In this video, we are moving on to section 4.1 titled Solving Systems by Graphing. And by systems, they mean systems of equations. So up until now, we've been working with a single equation, graphing them to see what it looks like as a line, if it's a linear equation. And now we'll be looking at multiple lines at the same time. So we'll see what it means to solve them and what this looks like from a visual perspective in terms of their graphs. So first, let's just see how we can tell whether an ordered pair or a single point is a solution of a system of equations. So the definition from the textbook says a solution of a system of two equations and two variables is an ordered pair that is a solution of each equation in the system. If you remember previously when we had an equation of a line, we were able to tell if a point was a solution by plugging in that coordinate point, and each coordinate point gives you an x value and a y value. By plugging in that x and the y into the point to see if we get a true or false statement. And then visually that told us that that point, that coordinate point, was on the line that the equation was describing. So if we have a system of equations, and we'll be looking at systems of two equations, but you could have any number of equations. For a point to be a solution to the system, it would have to be true for both lines at the same time. So basically, we just plug it into both lines and see if it's true in both cases. So let's see that here. We're going to determine whether the point 2, 3 is a solution for these two systems. So let's look at the first one from part A. And I'll take one line at a time and plug in, this will be our x value of 2 and a y value of positive 3. So our first equation in part A is y equals x plus 1. So let's plug in 3 for y and 2 for x. So 3 equals 2 plus 1. Yeah, 3 equals 3. That's a true statement. But let's look at the second equation. We have x plus 2y equals 8. So let's plug in 2 for x and 3 for y. So this would be saying 2 plus 6 equals 8, or 8 equals 8. Also true. So because it's true for both of the equations, we would say that this point 2, 3 is a solution of this system. So let's try the same thing with the two equations from part B. The first equation is 4x minus 5y equals negative 7. So let's plug in 2 for x and 3 for y. So this will give us 8 minus 15 equals negative 7. And 8 minus 15 is, in fact, negative 7. So this is true. Okay, let's try for the second equation. We have 3x plus y equals 4. So let's plug in 2 for x, 3 for y. So this says 6 plus 3 equals 4, or 9 equals 4, which is definitely not true. This is false. So while it was true for the first equation, it was not true for the second equation, so we cannot say that it's a solution for the system overall. So I'll say 2, 3 is not a solution. So if you're just given a point in a system and asked whether it's a solution or not, you can try plugging it in, and if it's true for both, as was the case for part A, you can say it's a solution of the system. But what does this mean? What does this mean when we say it's a solution of a system of equations? Well, we're saying that it's true for both at the same time. And we had said previously, for a point to be a solution to an equation, it means it's a point on the line. So if we have two lines that we're looking at, let's look at this visually. So let's skip to the next section. So this is solving a linear equation by graphing, or solving a linear system by graphing. So if we have two lines in space, because each equation in a system will represent some line. So let's say we have some line like this, and then some line like this. They intersect at some point. There's some point in space here that is on both of the lines at the same time. And I can just call this x comma y. So this point of intersection is the solution of the system. Or to say it another way, if we show that a point is a solution to a system, it means that is the point where the two lines intersect each other in 2D space. So that's what they're describing here in the definition. It says when solving a system of equations by graphing, the point of intersection is the solution of the system. If a system has at least one solution, we say that the system is consistent. The equations are independent if the system has one solution. So just to add some additional terminology. So let's apply this idea of the point of intersection between two lines. Let's look at example 2. So we have two lines here. Let me write out what we have. Y equals 1/3 x minus 2. This is a line in slope-intercept form, so that will be easy to graph. This is line 1. And then our second equation, we have 2x plus 3y equals 3. This one's in standard form. Let's convert it into slope-intercept form so that we can read the slope in the y-intercept and graph it very easily. So remember, slope-intercept form is in the form y equals mx plus b. So it's solved for y, where m is the slope, and b is your y-intercept. So like in this first equation, we know 1/3 is the slope, -2 is the y-intercept. And we'll use that in a second. So let's solve this equation for y. Let's subtract the 2x over, so 3y equals -2x plus 3. And then we'll need to divide everything by 3. So this will become -2/3 x. 3 divided by 3 is +1. So this will be our second line, line 2. So let's graph these two and see where they intersect. Let me produce some axes here. Add some marks. All right, this is our x and our y axis. So the first line, remember to graph in slope-intercept form, first plot the y-intercept, so y equals 1/3 x minus 2. So our y-intercept should be here at -2. And the slope is positive 1/3, so I'd go up 1 and then over 3. So I should end right here. That looks like the point +3, -1. And then I'll connect these with a line. So we have our first line. Let's graph the second one now. This one has a y-intercept of +1 and a slope of -2/3. So I'd go down 2 and then over 3. Notice we end up in that same point again, the 3, 1 point, or 3, -1. So let's connect this. So we have two lines, and this one worked out pretty nicely where we can tell where they intersect. It might be more difficult sometimes if they're intersecting at some fraction or decimal in between values, but this one was set up pretty nicely. So we see that they're intersecting here. So I would say that that coordinate point, 3, -1, is a solution to this system. It is the solution, actually. This one has a single solution. So if you're able to graph them easily, you can visually see where they intersect, and that will tell you where they have a solution. And I mentioned this is the solution. This has a single solution, but that's not always the case. So let's look at a couple special cases where things might be different. So there's a few special circumstances we can find ourselves in. So the first is what we just saw. I wouldn't call this special, but this is one version, and it's very common for two lines to intersect at a single point. So I could have one line like this, and let's say our second line is like this, kind of like what we just saw. They intersect at a single point here. In this case, I'd say the system has exactly one solution. But what else can we have? Think about some other types of relationships between lines that we've seen. Well, two lines can be parallel to each other. I can imagine I have some line like this, and then another line like this. They're parallel. Parallel lines have the same slope. These lines will never intersect each other. So to keep with our description of a solution being the point of intersection, if two lines are parallel, we would say that they have no solution. There's no place where these two lines will intersect, at least on a two-dimensional surface. And we could have two equations that we're looking at that end up graphing the same line. So I can imagine one line and then the second line is just right on top of it. In that case, every single point on the line would be a solution to the system because every point is on both lines. You could say they're intersecting at every point. So this would be a case where we would say there's infinitely many solutions. Every point on the line is a solution of the system. So let's read through a couple definitions that we have from the textbook. It says when solving a system of equations by graphing, if the lines are parallel, then the system has no solution. And so they use this term for the empty set, meaning the solution is a set containing nothing. There is no solution. Furthermore, a system that has no solution is inconsistent and the equations are independent. The second definition says that when solving a system of equations by graphing, if a graph of each equation is the same line, then the system has infinitely many solutions. The system is consistent, and then we would describe the lines as being dependent because they are the same line. So if it has a solution, it's consistent. If it's the same line, they're dependent. If they are different lines, we'd say they're independent. So they suggest this procedure for graphing, solving a system by graphing. Oops. It says if the lines intersect at a single point, the point of intersection is the solution, the system is consistent, the equations are independent. If the lines are parallel, the system has no solution. We use the symbol for the empty set. System is inconsistent, and the equations are independent. If the graphs are the same line, there's an infinite number of solutions, the system is consistent, and the equations are dependent. So lots of terminology they're introducing here. Let's focus first on how many solutions equations have. Let's look at this first example. It wants us to solve by graphing. So let's put these two equations into slope-intercept form. Let's look at the first one. We have negative 2x minus y equals 1. So let's solve for y. I will add the 2x over to the other side. Divide by negative 1. It's going to flip the sign of everything. And that's our first line. So let's go ahead and stick that on the graph. We'll do these one at a time. So this has a y-intercept of negative 1 and a slope of negative 2. So we'll go down to over 1. So something like this. Now our second equation, we have 2x plus y equals 3. Let's solve for y. I'll subtract the 2x over, so it'll be minus 2x plus 3. Notice these two lines have the same slope. That was an indication we saw previously that two lines are parallel. So this has a y-intercept of positive 3 up here, and then also a slope of negative 2, so down 2 over 1. This might look a little bit off due to my spacing, but they have the same slope, so I know that they are parallel. So they will not intersect in any point that we can see here. So we'd say the system has no solution. Or we use their symbol. I think the dash technically goes the other way. That's a result of me being left-handed. Okay. We didn't even really have to graph. We could just see that the two slopes are the same. They both had a slope of negative 2. That's a giveaway immediately that there will be no solution. All right, let's look at another example. They give our first line in slope-intercept form, so that's good. We have 2/3 x plus 2. And then let's put our second line in slope-intercept form as well. 12y minus 8x equals 24. I'll add the 8x over. This will be positive 8x plus 24. Then we will divide everything by 12. So 8 over 12x plus 24 over 12. That first fraction, let's divide everything by 4. 4 goes into 8 2 times and into 12 3 times. And then 24 divided by 12 is 2. So notice we have the same equation. So even without graphing, I know there's going to be infinitely many solutions. And we can produce the graph, but let's just jump to the conclusion here. These are the same line. It wasn't as obvious at first because they're in two different forms. This is the line in slope-intercept form and the line in standard form. But they are in fact the same line, and we showed that by turning the second one into slope-intercept form. So there are infinitely many solutions. So how should we express this? Well, we can use set builder notation. This will look a little bit different. So we said a solution to a system is a point. So we'll say the solution set is the set of all points x comma y such that, and we can just give one of the definitions of the line, such that y equals 2/3 x plus 2. That means any point that's a solution for the line, any point on the line will be a solution to the system. So we're describing an infinite number of points here. Pretty useful notation. All right, so let's use this, let's continue this idea of checking out the slope or seeing if it's the same line to determine if we have no solution, one solution, or infinitely many solutions. So we can do this without even graphing. So let's look at these three examples. So our first example, part A, they give our first line in slope-intercept form. And notice I'm just converting these to slope-intercept because that's an easy way to tell. We can look at their slopes to tell if they're parallel, or if they're the same line, they will appear the same. Or if they have different slopes, then we can say that they will intersect at some point. So let's turn this second expression, 5x plus 8y equals -8, into slope-intercept form. So I will subtract the 5x over, and then we want to divide by 8. So this will give us -5 over 8x minus 1. So 8 divided by 8 is 1. So I have two lines. They have two different slopes, which means that they're going to just intersect at some point. We don't know what point it is. We could find out by solving. We'll do more on that in our next video. But for now, we can just say we're going to expect to have one solution, because we have two different lines with different slopes. All right, let's look at part B. Let's turn both of these into slope-intercept form. I have 4x minus 8y equals 10. So I will subtract the 4x over, -8y equals -4x plus 10. Divide by -8, so -4x over -8 plus 10 over -8. The first term will reduce to 1 over 2. The negatives will cancel, and this will become minus, and let's divide each of those by 5. Or no, by 2, I mean. 10 divided by 2 is 5. 8 divided by 2 is 4. It's about as reduced as we'll get. So there's our first equation. Let's look at the second one. We have -6x plus 12y equals -15. So let's add the 6x over, so 12y equals positive 6x minus 15. And then let's divide everything by 12. And then reduce. So 6 over 12, that will reduce to 1 over 2. 6 goes into itself once, and then 12 two times. And then the second number, let's divide everything by 3. 3 goes into 15 5 times, and into 12 4 times. So notice we have the same equation, 1/2 x minus 5 over 4, 1/2 x minus 5 over 4. So this will have infinitely many solutions. So we got the same line. Let's look at part C. So let's start with the first equation, 9x plus 6y equals negative 13. I will solve it for y, so 6y, let's subtract the 9x over to the other side, and then divide by 6. The first term, we can divide both of those by 3. 3 goes into 9 3 times, into 6 2 times. And we have to leave the 13 over 6. So let's look at our second line. 3x plus 2y equals 4. Let's subtract the 3x over and then divide by 2. So negative 3 over 2x plus 2. The y-intercepts are different, but notice the slopes are the same, negative 3 over 2. So the slopes are the same. That's a giveaway that they are parallel, and thus we will have no solution. So if the question is just asking you to determine how many solutions you have, if you get two different lines with two different slopes, you'll have one solution because they will just intersect at a single point. If you get the same line, so they reduce to the same equation, there'll be infinitely many solutions because every point will be a solution. Or if you get two lines that have the same slope but different y-intercepts, that means they're parallel. Notice these two had the same slope as well, but the y-intercepts were the same, so that made them the same line. So to be parallel, you need to have the same slope but different y-intercepts. And if that's the case, there's no solution. All right, I think that's it for this section. This was a shorter one. So we're taking a visual approach to solving a system of equations. So we determined whether an ordered pair was a solution to a system by plugging it in, seeing if it makes both statements true at the same time. We solved a linear equation by graphing, finding the point of intersection. There were the special cases of being parallel or the same line. And then we used those ideas in order to determine the number of solutions that a system will have. All right, that's it in this video. Next time we'll look at some more analytical ways of solving a system of equations. Okay, I'll see you then.